Hello, this is Tracy. Welcome back to Math 135, and we are still going over section 4.3, binomial distribution, and we have another example here from a different stats textbook than ours. I love our stats textbook, but it doesn't have as many of the nitty-gritty studies, real-world applications. So, got that from another textbook. Here we are talking about the Helsinki Heart Study. And this asked whether the anti-cholesterol drug gemfibrozil reduces heart attacks. In planning such an experiment, researchers must make sure the sample sizes are large enough to allow them to observe enough heart attacks to draw conclusions. This study planned to give gemfibrozil, I think that's how you say it, to 2,000 men aged 40 to 55 and a placebo to another 2,000 men in the same age group. The probability of a heart attack during the 5-year period of the study for men this age is about 0.04. So we need some correct notation to describe this binomial experiment. So first of all, we need to decide what our random variable x would be. And in this situation, we are looking at heart attacks. So x is going to be the number of heart attacks. And if you are in the medical field, myocardial infarction is our abbreviation for heart attacks, for those of us who are too lazy to write out the words heart attack. Okay, so this is a binomial experiment. X is a random variable that follows a binomial distribution. How many people are we looking at? Just do one group at a time. So we're going to have 2,000 trials, 2,000 people whose results we look at. And what's the probability of success? Now remember, success is not a good thing. Success is having a heart attack, because that's what we're looking at. How many heart attacks? The probability of having a heart attack? 0.04 for men in this age group. So here's how we would use notation to describe our binomial experiment. What is the expected value for the number of heart attacks in each group of 2,000 men if the drug doesn't do anything? It doesn't change the probability of a heart attack. Well, in this case, the expected number of heart attacks, mu, is going to be the number of men times the probability each one of those fellas has a heart attack. So we have 80 heart attacks expected in each group. Does the number of men we expect to see with heart attacks seem to be large enough to draw conclusions? If you are expecting to see 80 people in each group, that should be enough that you can tell if the drug's doing anything. You should get a significantly lower number. So yes, 80 people is enough to compare how many heart attacks in each group. So if we have a study being this size like we want to, our standard deviation is going to be the square root of NPQ, square root of the number of people in the study, times the probability of a heart attack, times the probability of not having a heart attack. Remember, Q is going to be 1 minus P, because probability of success plus the probability of failure is 1. So 1 minus 0.04 is going to give us a 0.96. And again, pop that in your calculator, and we have a standard deviation of about 8.76 heart attacks. Now, in our actual study, hopefully I have enough room to do all this. In our actual study, we didn't have exactly 2,000 men. In the placebo group, we had 2,035 men, and there were 84 heart attacks. Seems reasonable. A little bit more than 2,000, a little bit more than 80 heart attacks. Plus, with the standard deviation we see of 8.76 heart attacks, this is less than one standard deviation away from how many we expect. That's not a big deal. In the treatment group, we've got 2,046 men, and 56 had heart attacks. This seems kind of low. let's see if it's unusually low. So first of all, we need to redo our expected number of heart attacks in a group of 2,046 men. So 2,046 times 0.04. Pop that in your calculator, and we find out that we have 81.84 heart attacks expected. We expect 81.84 heart attacks in this group of 2,046 men. And our standard deviation is going to be the square root of 2,046. If this drug does nothing, then the probability of a heart attack we still are thinking is 0.04, and the probability of not having a heart attack is 0.96. So we do our calculation and we get a standard deviation of 8.86 heart attacks. Now we want to know if 56 is unusually low. If our treatment does nothing, would 56 be a crazy number of heart attacks to get? Well, remember that a number is unusually low if it is more than 2 standard deviations below the mean. So we take our mean, we subtract 2 standard deviations. That result and lower is unusually low. So we expect 81.84 heart attacks. We take away 2 times that standard deviation, 8.86, and we wind up with, pop that in your calculator, 64 heart attacks and below. 64 heart attacks and below is unusual. That is unusually low. So 56 heart attacks, that is below 64. So yes, this is unusually low. So what this tells us is that either the medication does nothing and we got some crazy group with an unusually low number of heart attacks, just my chance. Not very likely. Or our assumption about the probability of having a heart attack in this group is wrong. It's not 0.04. The probability of having a heart attack in this group is actually lower. The gemfibrozole works. Either the gemfibrozole doesn't work and we just got a freaky, weird, unusual group with an unusually low number of heart attacks, or the gemfibrozole works and the probability of having a heart attack in this group is lower than 0.04. Alrighty, we are going to end this video, and in the next video we will finish up section 4.3.